that's, yeah. So now what we have is our conventional entropy when temperature approaches 0 K. We have S0 equals to 0. Our next goal here is how to calculate entropy change at constant pressure throughout the process. All right, so the overall, the general reaction we'll be using is this delta S naught equals to the integral of Cp over T dt. And that's where it comes from. And we'll look at a reaction, a hypothetical reaction of water, solid water at 0 K, will gradually change its form, change its phase, change its temperature until we reach a point of the water in your thermodynamics table. And actually it should be 1 bar, by the way. All right. So if you think about the process, these are solved problem. We're just trying to use what we did before in the actual setup of the thermodynamic table derivation. So what are we doing here? We start by changing the temperature of my water in its condensed form or solid form. So this part I call it A. We increase the temperature of water to its melting point at that 1 bar of pressure. Right, so it's all solid phase. You're just increasing the temperature without any phase transfer and calculating delta S of the temperature increase. And secondly, what we have here is melting, right? So the solid liquid, the solid water will melt into liquid water at its melting point. Presumably, it's a reversible process since it's at the melting point, and that's our B. This should be A, by the way. And at last, we want to increase our temperature to where our thermodynamic table is, whether it's 298 Kelvin, 313 Kelvin, doesn't matter, depending on what format of your thermodynamic table you're using. And that's our process C. And are these solved problems? Like, let's see if we know what are these. Now, problem A, we're having the isobaric temperature increase of solid water. All right, so that's something we already did. It's isobaric temperature increase. So my delta SA equals to the temperature between 0 to T melting, and Cp, or the isobaric heat capacity of your solid water at over temperature dt. Or for the specific process A, the delta SA is also defined as the molar entropy of your solid water at T melting, H2O solid, minus your S0, which is 0. Right, so product minus reactant for your process A. What about process B? Well, so we're looking at a isobaric melting or reversible phase transfer. So what do we know? It's the same, right? So we're talking about the isobaric phase transfer. So that's just the delta H of melting. So my delta SB equals to the delta H melting of H2O solid into liquid over the melting point. And also, like the process B is also defined as product minus reactant. So my delta SB equals to the molar entropy at T melting of your H2O liquid minus the molar entropy at T melting of your H2O solid. All right. And what about C? C is effectively the same as our process A. That's a isobaric temperature increase now for my liquid water. So process C, that's your isobaric temperature increase of liquid water. So we can write that as delta SC equals to the T melting into, well, T final, whatever the final temperature we want it to be. That's the CPm naught H2O liquid over temperature dt. And also product minus reactant, that's the standard molar entropy of your final H2O liquid at temperature final minus S naught m T melting of H2O liquid. All right. So if we think about the overall process, what are we looking for? We are looking for a difference, or the delta S, between your final state and your initial state. So we're looking for my delta S equals to the molar entropy of my H2O liquid at T final minus 0. Right, so the overall delta S is something we went over that equals to delta SA plus delta SB plus delta SC. And in the processes, there are several intermediate states that will cancel out themselves. Like, for example, this one we have the T melting, the SM, the molar and standard molar entropy of your water solid at melting point, which is canceled out here. So these two will cancel out. Likewise, the standard molar entropy of your liquid water at melting point will also cancel out when you add like A, B, and C together. Right? So overall, when we add the A, B, and C together, we end up getting this is what we want, the standard molar entropy, standard conventional molar entropy of your liquid water at temperature that we desire, minus S0. Or if we write all these equations together, we end up getting the expression. Let me put it on the board. Okay. We end up getting the expression of your conventional molar entropy at 1 bar, certain temperature, equals to my delta SA plus delta SB plus delta SC. And that equals to your 0 to P melt, and we have CPm naught H2O solid over temperature dt plus delta H naught melting over T melting of your H2O solid to liquid, and plus your T melting to T final C naught PM H2O liquid temperature dt. All right. So these should be things we already went over. Like, that's why we spent a good amount of time in our previous lectures talking about how to calculate entropy for like isobaric temperature increase, how to calculate entropy for reversible phase transfer at constant pressure. Like, I just want to make a connection with something we discussed in previous chapters when we introduced entropy as a state function. And now observing these relationships, some of the things is a little bit trickier for us to calculate, which is this part. Now, experimentally, we can measure the isobaric heat capacity or molar isobaric heat capacity by measuring how much heat is being transferred and how does that heat correlates with temperature, right? But there's a problem in this relationship. That is the Cp naught, the molar isobaric heat capacity at a very low temperature, meaning like 0 to 15 K, that's above what our experimentalists can measure. Now, it's really hard for us to get it down to 0 to 15 K already. It's even harder to measure how does the heat correlate with temperature. All right, so this part, we'll have to further break it down into two sections, which is one, the 0 to 15 K, or we say that's the low temperature of your Cpm naught over T dt, and then the temperature between 15 K to T melt of your Cpm naught over T dt. So this part is something we can get by experimental measurement. So we're just going to focusing on this low temperature isobaric heat capacity for now. So what does it mean? So in this case, what we say is that from statistical mechanics, when temperature is very low, scientists use statistical mechanics to approximate what is the heat capacity. So this is what we end up getting. It's the molar heat capacity. We sometimes call it T low. So this T low is effectively saying that's temperature lower than 15 Kelvin. That's roughly equal to the CV. So the CV and CP becomes equivalent to each other at very low temperature. And that's roughly equal to a constant times T to the cube. So don't ask me how that's being derived. It's a little bit beyond this class. But for this class, just knowing we have this expression of the standard isobaric molar heat capacity at very low temperature, meaning temperature is smaller than 15 Kelvin, it's roughly equal to a constant times T to the cube. Yes.
CV is exactly equal to A times T to the cube?
So with that in hand, we can simplify this relationship a little bit, right? So for our purpose, we are rewriting the integral from 0 to T melting point equals to my Cpm naught of H2O solid over temperature dt. We're rewriting that into 0 to 15 Kelvin. Low temperature heat capacity, which is the AT cube over T dt, and plus the 15 Kelvin to T melt Cpm naught over T dt. And this term, just a little bit of calculus, we can simplify that into A times 0 to 15 Kelvin T squared dt, or that's like a T cube over 3 from 0 to 15 K, or you can rewrite that as 3 AT cube, or actually that AT cube just equals to your Cpm T naught of T low divided by 3. All right. So far what we end up getting is for any processes or for any chemical substances we care about at this 1 bar of pressure, and then say 298 Kelvin, which is the number we want in the thermodynamic table. We build up a way to connect that conventional molar entropy to an expression that can be experimentally measured. And let's look at one example question together, a very comprehensive example involving the actual measurement of a species and measurement of its conventional molar entropy. So one day I'll replace this one with the actual screenshot from the table, but bear with me a little bit. So here is the example 5.7. It's a very, yes?
I had a question on the thing previously. Just to be sure, the CPM you're talking about is for the H2O solid. You're just taking it in different columns because you want to include the 0 to 15 Kelvin.
Right. So in this case, we're just talking about for some species. Right? I'm using H2O as an example.
Okay.
Yeah, but it can be any kind of species you want to talk about. It's just like, for example, these. Well, we'll see that in the experiment. Like, for example, in this case, now we're dealing with SO2, which we're giving you a lot of information, including melting point, normal melting point. So that's a melting point and boiling point at your 1 bar. So the normal melting point and boiling point is given 197.6 Kelvin, 263.1 Kelvin. Also give you the heat of fusion and vaporization for SO2. So you have the delta H for phase transfer. And also, that's the heat of fusion and vaporization at normal melting and boiling point. We'll also give you a graph of the CPM at 1 ATM. Wait, 1 ATM is actually normal, okay. So normal and standard are also different, but this one is normal, which is the 1 ATM. So this one we're telling you that the CPM at 1 ATM is graphed versus the natural log of temperature in the figure here. And from 15 to 298 Kelvin. Again, remember, we don't do that experiment below 15 Kelvin. And at 15 Kelvin, we're giving you that the CPM equals to 0.83 calorie per mole per Kelvin, or that's the low temperature CPM we were talking about before. And these data were actually coming from a published manuscript from 1938, which is a little bit time from now, but nevertheless. So these were actual experiments that scientists did a few decades ago. And we also tells you the entropy change of converting ideal to real gases at 298 Kelvin and 1 ATM. And the question asks you to estimate the standard conventional entropy of SO2 gas at 298 Kelvin. So we'll set up this problem together. I probably don't have time to do all the calculation with you, but I can set it up with you. So let's think about this process. What are we looking for? So again, in this whole process, there are several things we know, and we want to think about what we have and what we want to use. Now, first of all, in this process, we need to have some information with my CP. All right. So in this case, what do we have? We have a plot of your CPM versus the natural log of temperature. So what do we know about natural log of temperature? So here is the thing, a little bit of calculus. So the differential of your natural log of temperature over dt equals to 1 over t. So what does that mean? That means if we're taking the integral of your CPM over t dt, that's effectively in working, right? So in this case, what are we getting? It's your d ln t equals to 1 over t dt. Or in this case, what are we getting? It's the integral of your CPM d ln t equals to our somewhere CPM over t dt. And what else do we get from here? What we know is that the integral, you can vaguely think about it as a measurement of the area below the curve. All right, so in this case, what are we saying is we're transferring this expression of saying, okay, so the integral of my CPM over t dt is the area below the curve of my CPM versus ln T. All right, and in my figure, we look at the y-axis, that's my CPM. My x-axis is the natural log of temperature. And if we want to have an estimate of this integral of my CPM over T dt, we're just looking at the area below the curve. And that's something we can solve by approximate the curve to be some kind of like a triangle, so bottom times height times 1/2. All right, so that's solved. So we have this part solved. I'm just looking at this. So we have this part solved. It's the area below the curve. We have also this part solved, also the area below the curve, right? So we're looking at the temperature here. So in here, this is roughly your 15 Kelvin, and this is your normal melting point when the solid becomes liquid. That's your normal boiling point where your liquid becomes gas. Or if I actually put those labels on here, this is your 15, it's a bit too big. This is your 15K mark. And this point where your solid becomes liquid, that's your T melting. And where your liquid becomes gas, that's your T boiling. And the end point is where we want, which is the 298 Kelvin. And we can read those numbers from like what's the melting point and boiling point and put it onto the graph, right? So the melting point is 197.6 Kelvin. Boiling point is 263.1 Kelvin. All right. And I'm gonna set up this problem with you on the board to see like for this kind of problem, what's the best way to do it without making mistakes? It's very easy to make mistakes. So I'm just gonna do it in a stepwise version. So this is a little bit like what we did when we do this delta SA plus B plus C. So for this question, you want to write out everything specifically so that you know what delta S you're calculating. So our starting point is our reference point. So at the original point where my temperature is about 0K, right, or my S0. So that's my solid form. The second state is we want to increase my temperature to 15K, still solid. And for this process, we're using this equation, the one we just derived, which is my delta S from 1 to 2 equals to your CPM naught, T temperature, T low, divided by 3. So that's something we just derived. We're using the isobaric molar heat capacity at low temperature, and that number is given in the question. And now from 15K solid, we want to increase my temperature to my melting point. Still solid, so it's a isobaric temperature increase. The equation we want to use for this part is your integral of 15K to 197.6 CPM naught over T dt estimated by the area. So if we go back to the actual figure, what's the actual shape we're looking after? Right, so we're talking about solid phase, increasing the temperature between 15K to my T melting. Or this is effectively the area below this one. You can estimate it as a triangle. And that's just, I actually forgot that word. But you can estimate it as a triangle, so bottom times height and divided by 1/2. And let's keep going. Right, so next step, we have melting taking place. So still temperature equals to 197.6 K. So at my melting point, but now we're at liquid phase. So for this process, we're using the delta H of melting, or the heat of fusion, to estimate how much entropy is calculated. So this one is delta S 3 to 4, so melting. And that equals to delta H of melting over T melting. All right. And what are we doing is we'll keep going, right? So then we have, again, in the liquid phase, we have temperature increase again. So for process 5, we want to increase my temperature into vaporization point. Still liquid. And likewise, you want to vaporize it to gas phase at your vaporization point. And also, here is real, by the way. We're doing the experiment, so everything is real. And you should know how to do those calculations. It's the same idea, right? So for temperature increase, we're estimating it by the area below the curve. So that's going to be this one. And then for phase transfer, you're using the delta H for phase transfer divided by the vaporization temperature. And from 6, again, what's next? Next up, you want to increase it into our final temperature, which is the 298 Kelvin. So for our real gas phase, we get it to temperature equals to 298 Kelvin, again, estimated based on the area below the curve. So area estimate. Area estimate. This one below is delta H over T. And now we get it to my real gas at 298 Kelvin. 1 ATM, by the way. So everything here are like all 1 ATM. So everything on the figure is like at 1 ATM. But do we stop there? Like, be careful with it, right? Because this question is asking us for the standard conventional molar entropy of your SO2 gas. So this is a point of easy miss. It's standard state, right? So what is the standard state of my S2O gas? It's ideal gas. So that's why the question gives you this transformation between ideal gas to real gases. All right, so this is one of those points. You're reading the question and be like, I didn't use this number. Where does that come from? That's where it comes from. Because the experiment was done for real gases, but for standard state, we want to convert it into ideal gas. And one more trap in this question. The standard state, we have this little knot. So this little knot tells me that P equals to 1 bar, and gases are ideal. So 2 more steps, right? So first step is we want to transfer that into gases are real to ideal. My T equals to 298 Kelvin, pressure not equals to 1 bar. So this part is your pressure change or isothermal pressure change of your ideal gases. So once you change your real gas into ideal gases, that isothermal pressure change is something we discussed before. All right. So this is one of those questions that looks super long. It is super long, actually. It's going to take you a lot of time. But the logic behind the question is not that complicated. I mean, everything here are things we discussed before in chapter 3. Now, this is just a comprehensive example of using everything we discussed so that scientists can get to our thermodynamic table. That's how these numbers come from. All right, so we'll pick up from here of like finishing up chapter 5 in how to use thermodynamic table. And later on, we'll talk about reaction equilibriums and more chemistry effectively. All right, see you next Wednesday. No class next Monday.